So hi everyone, it's a pleasure with Sven to share this session 9, named New Applications. And so let's start with the first presentations given by our colleagues Nils Bartels from DLR.
Hello. So my name is Nils from DLR in Stuttgart. I'm going to present on polarimetric satellite laser ranging. This one doesn't work. Can you help me? You have to press down. Okay, thank you. Okay. So, as I said, I'm from Stuttgart. We hosted the last SLR technical workshop in 2019, and I enjoyed this workshop a lot, and it motivated me to do some more work on satellite laser ranging, and so I'm here. We had a very interesting talk in this morning from Tim Flora, and so I won't have to say much about this topic. So our motivation is actually that we want to do SLR for the application of space traffic management. So it's not directly the purpose of SLR, how it was developed, but it's a new application. And there's a highly increasing number of objects in space, especially in the low Earth orbit. And there are many collision avoidance maneuvers every year. And the interesting thing about it is that actually most of these collision avoidance maneuvers, they wouldn't be necessary. So they are false alerts. And SLR, as it's a very precise technology, has the potential to greatly reduce this number of false alerts, and that's the number of necessary collision avoidance maneuvers, which can save money. Another problem is that especially when you have cluster launches of several satellites starting with one rocket, there is a problem to identify these satellites. So even, this is shown in this plot, even let's say 100 days after a launch, it's often the situation for these cluster launches that only, let's say, 70% of the satellites are identified. And so there's research on solving these problems. One of the solutions is to use like coded light signals, like pulsed LEDs. This is called extremely low research optical identifier. And other idea is to use radio transmitter. This is the qubit. This is also like an experimental project. But what in this community we are interested in is satellite laser ranging. And as one can see, in principle, there is some opportunity already for the identification. So if you have two retroreflectors and the satellite is not directly pointing towards the SLR station, you get a range difference, and you can at least see that there are two retroreflectors mounted to the satellite. But the question is, of course, how can we increase the number of IDs? And there are different ideas, so you can use color, maybe intensity, so you could have like a big retroreflector next to a small one. And another idea is to use the polarization of light. Actually, this idea is not completely new, so there was a talk here at the ILS workshop in 2018 from Andrei Sokolov. And he suggested to use polarization. So here you can see you have a circularly polarized light coming in. You would have, let's say, a quarter wave plate, which would turn this circular polarization into linear polarization. And then you have a polarizer. And if this polarizer is aligned with the polarization of this light, it would be transmitted, and otherwise it would be blocked. So you would have some sort of possibility to distinguish these retroreflectors and thus maybe satellites. But of course you can try, and that's what we've been thinking of, to push this even further. So you have this basic setup of two polarization optics mounted to a retroreflector. The central optics could be a polarizer, or it could also be a second quarter wave plate. And then you have a certain orientation angle between the optical axis of these two elements, and we want to try and retrieve this information from ground. And yeah, for this, just some very basic definitions. We can always emit either right circular or left circular light, or we can detect the right circular and left circular components of light. So we would measure 4 intensities, and with these intensities one can define certain symmetry parameters that would sort of describe our assembly that consists of polarization optics and a retroreflector. And so what we've tried is we define a set of 7 retroreflector assemblies with different polarization type of optics in the center and different angle alpha, which describes the orientation between the polarization optics. And we've done some testing in the laboratory on this, which I'll go into the next slides. But what is basically the idea is also that you cannot just have one retroreflector, but in case you have 2, then you could have even more combinations, because you can still see which is my retroreflector, which depends on the range. And so you can basically generate an ID of several retroreflectors. For example, if you have 3 retroreflectors and you would have 7 assemblies, you can calculate that you would actually have you would have 84 IDs used for satellite identification. So now, as I said, it's on a laboratory test level at the moment. The first experiment is you basically set this up, these assemblies, and you just measure the total intensity. And from these, you calculate these what we call symmetry parameters. And here you can see basically the calculation, how they are supposed to look like from theory. And then you can see the experiment. It fits pretty well. So the arrow bars, they mostly come if you rotate these assemblies. You introduce certain errors, because, for example, a quarter wave plate is not exactly a quarter wave plate if you tilt it. So that's where these arrows come from. But still, you are able, or we are able to distinguish these 7 assemblies. What makes SLR difficult is that you won't actually detect the total intensity coming back from a retroreflector, but what you actually detect is the far field diffraction pattern. So what we've also looked at is it possible to measure the symmetry parameters actually in the far field diffraction pattern? So we would actually have a setup in which we can measure the far field diffraction pattern, and then we basically build these different setups, we rotate them, and we always generate the pictures of the far field diffraction parameter patterns depending on the detected and the emitted polarization. And yeah, as we can see here, we find that it's actually possible to detect this. So here in this assembly, for example, here this intensity goes to 4,000. So this is one example where you get most of the intensity if you emit left circular polarized light and you detect right circular polarization. And even though in this plot it only goes, I think, to 50, you detect almost no intensity, you get about the same far field diffraction pattern, which shows that it's feasible to detect these symmetry parameters in the far field diffraction pattern. So the last thing I want to talk about is how could something like this be actually implemented into an SLR station. So we actually built a setup that is close to an actual SLR station, but it's still a laboratory setup. And we think about how to switch the polarization. And one opportunity for doing this are what are called liquid crystal variable retarders. So these are basically polymers that when you apply a voltage, they will get to a different orientation and thereby change the polarization properties. So they can be switched in the IR on a time scale of about 50 milliseconds. And so you could have basically a liquid crystal variable retarder in the emitter and one in the receiver, and use this for the detection. Would probably be easy to integrate into the SLR setup, but it also has some downsides. So for example, it needs to be calibrated. It also needs to be temperature stabilized. And during the switching time, you would have a not defined polarization state. So because of that, you would have to do some filtering of the data. And also, if you switch, you actually have to switch the receiver after the emitter, which makes life also a little bit more complicated. So we came up with a second idea, which is presented here. So instead of using the liquid crystal variable retarders, we could use polarizing beam splitters. So part of the light would be transmitted in the emitter and part of the light would be reflected. So by this you actually get a double pulse and then you have a quarter wave plate, and then you would basically generate a double pulse with a certain delay where one of these pulses would have one polarization state and the other one would have the other polarization state, in this case right circular and left circular polarization. This light would go to a retroreflector, and then on the way back you would have basically another quarter wave plate and a polarizing beam splitter, and then you would have two detectors to detect the right circular and left circular components of the light. So in this way, you would actually have no parts that are moving or no voltages. Thank you. So that's the idea that we are working on now in laboratory experiments, and there's a PhD thesis that has just started on it. Okay, so as I said, we are investigating polarimetric SLR to allow for a simultaneous orbit determination and also the identification of satellites. This idea is targeting towards space traffic management, but it might be interesting to discuss with you actually if there are also applications that you are more interested in, so in anything in space geodesy. We heard talk about attitude determination, maybe it could be useful there. There's also the question, we know some people are here from industry. I would like to discuss if this could be an interesting idea for them, because it's clear that if you want to have an impact on space traffic management with this kind of idea, that you of course need like this to be distributed to a lot of satellites. And the last thing I want to say, I want to thank the entire team. I would also like to refer to an article in the Nature Communications Engineering, which is shown here. So in case you are interested in more details. Thank you.
Okay, so we have time for a few questions.
Thank you very much for that interesting talk. Have you given thought to the atmospheric effect of the polarization as you go try to range to these cubes? And also what, sorry, just a quick follow-up. In terms of uncoated cubes, they usually impart some circular polarization on return, which might scramble some of your identification. Have you investigated any of that?
So the first question, of course, the atmosphere can have some effect. So the way to deal with that is that's why we want to switch between the different polarization states quickly and do then, of course, an averaging of these measured intensities to basically reduce this effect of the atmosphere. It's also, for example, in quantum communication, the polarization is used for transmitting data, and there are also experiments in the literature where people have actually emitted a polarized laser from space, and on Earth detected on ground the polarization, and the polarization purity is actually quite high. So I think it's going to work, but of course we are on a low TRL, and it's something to test at the end. The second question, the change of polarization from the retroreflector is included in these ground-based tests. So the most important part is to use a metal-coated retroreflector, which is pretty good in preserving the polarization, whereas a total internal retroreflector, it introduces lots of changes to the polarization.
Right, but then you get some thermal effects from a metal coating, but...
Yes, this is also a possibility, so this is also something to look at, yeah.
Thank you.
Okay, another question? I don't see any. I have a quick one. In the end, it's just a game of detecting a variation of return intensity, if I got it right.
Exactly.
That's pretty difficult during operations, I guess.
You mean, why do you think it's difficult? Because the intensity is difficult to measure, or what's your...
No, it's just, I think it's just, or it depends on the satellite and the target, but we have variation, natural variation of return intensity on a regular basis based on many different things like pointing and so on, and that might be challenging to get a continuous return intensity to measure this.
Yeah, that's why you have to have lots of statistics for which you need high repetition satellite laser ranging, as for example in the mini SLR, and you need a high switching rate so that these effects, they average out. And the best thing for the statistics, I think, is if you basically have a double pulse, as described in our last experiment. And in that case, they are so close that you even freeze the atmosphere within this time frame.
Yeah, that sounds good. I don't know what the double pulse. Do you think that works with the gated detectors?
So this is something that depends on how wide is your gate, of course, and how long is your delay between the two pulses. But I think it works. Yeah.
Yeah, I'm not sure. Yeah, I don't know. Maybe you always get you get the first one a lot of times. Okay, but that's it.
Ah, yeah.
So,
okay, good.
Yeah, yeah. We continue later.
Yeah.